Hello and welcome to this video. My name is Saipan Kumar, where we will talk about a fascinating and innovative way of producing food and energy sustainably, that is agrophotovoltaic farming. This is a practice that combines agriculture and solar PV projects within the same area, using solar panels to generate electricity while providing a shaded environment for crops to flourish. Sounds amazing, right? But there is a catch. The shadow cast by the crops and other objects can affect the performance of the solar panels, resulting the decrease in energy. That's why shadow detection is crucial to ensure optimal performance of agro PV farms. In this video, we will explore how state-of-art neural networks can be used to detect shadows in agro PV farms. What are all challenges and opportunities for future research in this area? Let's get started. We understand why shadow detection is important. Let's dive into propulsion methodology. Use it to detect shadows in our study. We use three different approaches for shadow detection: GAN, encoder-decoder neural network, and object detection methods such as YOLO V5 and YOLO V8. First, let's talk about the encoder-decoder neural network approach. This approach involves two main components, an encoder and a decoder. The encoder phase involves convolutional layers with increasing number of filters and max pooling layers to extract significant features. The decoder phase uses upsampling to double the feature map size and several convolutional layers with reducing number of filters, ending with 1 cross 1 convolutional layer with a sigmoid activation functions to produce binary masks that represent detected shadows. Next, let's discuss GAN, or also known as General Adversarial Networks. GAN consists of two neural networks, a generator and a discriminator. The generator builds an attenuation mask to reduce shadowing data in input image. The output of generator network is sent to main network for evaluation, and the process continues iteratively until convergence. The discriminator in a GAN acts as a binary classifier to determine whether an input image and corresponding shadow mask are genuine or fake. It contains multiple convolution layers and fully connected layers to produce a single numerical value, indicating whether the input is real or fake. The discriminator function is crucial in ensuring that the generator mask by the generator minimizes the presence of shadows while preserving important features of the input image. Next, finally, we used object detection methods such as YOLO V5 and YOLO V8. These methods involve training neural network to identify objects in an image by drawing bounding boxes around them. We modified this approach to detect shadows by labeling the shadows as a separate class. Next, we move on to results and discussion section. The results section presents a comprehensive evaluation of performance of object detection models using various performance metrics. These metrics include computational cost, flops, mean average pressure, loss curves, FN curve, pressure recall curve, P curve, and R curve. The evaluation is conducted on YOLO V8 and YOLO V5 models, which are all trained for 100 epochs. The computational cost is measured to determine the necessary time and computing power for the neural network operation. The MAP, MAP50 and MAP5095 are used to examine the effectiveness of training process for object detection models. The FN curve is used to assess the effectiveness of object identification models and reveal information about trade-offs between precision and recall at various threshold settings. The result shows that YOLO V8 outperforms YOLO V5 in terms of its ability to accurately detect objects across different confidence thresholds. YOLO V8 consistently achieves higher precision and recall values than YOLO V5, indicating that it is better at identifying true positives while minimizing false positives. The higher area under PR curve, higher R curve, and higher precision and recall values in the PR curves for YOLO V8 indicates its superior performance compared to YOLO V5. The custom YOLO V5 model performance seems to be relatively subpar on the test set. with low precision and recall, as well as low MAP score. This is an example how prediction works in YOLO VA. See, in the first picture, it shows shadow of 62%, but in the second picture, it shows shadow of 88%. Meanwhile, it is not able to detect the shadow of this area. This shows object detection models are not fit for the shadow detection. In conclusion, the computer vision techniques have become increasingly popular in shadow detection. Our study evaluated the performance of different methods such as GAN, encoder-decoder neural network, and object detection techniques like YOLO V5 and YOLO V8 for detecting shadows. While object detection methods proved to efficient for the shadow detection, they may not provide the same level of accuracy as GAN and encoder-decoder neural networks. Our study found that YOLO V8 outperformed YOLO V5 in all metrics, making it preferred choice for shadow detection. However, we faced technical errors that prevented the implementation of GAN and encoder-decoder neural network, highlighting the need for further research in this area to address this challenge and explore the potential of these more precise techniques for shadow detection. Overall, our study shows that object detection methods like YOLO V5 and YOLO V8 can be useful for detecting shadows, although the results may not be as accurate as those obtained through the use of GAN and encoder-decoder neural networks. Additionally, YOLO V8 found, was found to be superior choice for this task. To conclude, further research is necessary to investigate the potential of GAN and encoder-decoder neural networks in shadow detection to address practical challenges associated with their implementation. Our study provides important insights to use of computer vision techniques for shadow detection and highlights area for future research. That's all for this video. We hope you enjoyed listening to the video and how AI can help us produce food and energy sustainably. Thank you for watching.